meet again this superposition, because this superposition, if in the DC circuit right now, you cannot see the advantage of superposition. Okay, let me give you some what we call brief explanation about what we will encounter in superposition when we have AC circuits inside. Okay, so for example, if you have this one, okay, so it's straightforward, right? So you have R, and then you have V source, and you need to calculate I. Okay, so if you have, right now we haven't really teach you about inductor and also capacitor. So inductor and capacitor is actually quite the relationship, or actually the properties of induction and capacitor is quite complex when referring to the resistor. Resistor is actually just a linear, because we know R is equal to V over I, so it's just a linear relationship. But for the inductor, the relationship of the voltage and current, okay, for example, the voltage across this inductor, this is not a what we call topic, okay? So this is just a briefing about what we will see in our AC circuit. Okay, so actually the relationship between the voltage and the current is not straightforward like resistor. It's actually the voltage across the inductor is actually the inductor value itself multiplied with the differential of the current over time. So this is, for example, this is the IL, the current that go through to the inductor. So it's actually a multiply with the derivative of the current. So as you can see, the relationship is quite complex. Okay, but usually we will not, in our AC circuit analysis, since this involves derivation, so we actually simplify the analysis. Okay, instead of using this one, we represent the AC circuit in what we call phasor diagram, in a phasor form. Okay, so instead of this one, so we didn't use L. Okay, so we have what we call X, JX. X is actually what we call reactance. Okay, and what is X? Inductor. This is actually J. This is an imaginary number multiply with omega and multiply with the inductor itself. So what is omega? So omega is 2 pi F multiply with F. Okay? Okay. So that's why so as you can see, the values of the reactance depends on the frequency inside the circuit. So right now, what is the frequency for this supply? DC supply. What is the frequency of the DC supply? Can someone? What is the frequency of the DC supply?
Over time.
Yes, that is actually the definition. But right now, what is the value? Frequency is actually in units, what called hertz, right? Okay, hertz.
Yeah, hertz.
You have been taught in your physics class, hertz, Hertz. Okay, hertz. So what is the frequency? So
50 hertz in Malaysia.
Okay, 50 hertz, but that one is actually AC. So you know that our grid is actually AC system. So this is a DC source. DC source. So the voltage is a constant. It's a constant voltage. is actually time independent of time. So it's constant. So when you have a constant, so meaning that your frequency is 0, right? 0. When you have a sinusoidal, okay, so this is your period, okay, period. So one cycle, positive and negative. So we have this one is period, and 1 over period is equals to. So in Malaysia, for AC system, we have the frequency of the AC is 50 hertz. Yes, correct. And Thailand is actually 60 hertz. It depends on the country. Japan mix, depends on the island. So Tokyo maybe 50 hertz, and then Okinawa 60 hertz. So the Japan have a variety of frequency supply. Okay, but Malaysia 50 hertz, and the Thailand is 60 hertz. So for the DC voltage source, so definitely this is a constant. So meaning that the frequency is 0 because there is no cyclic. There is no cyclic waveform here. Okay, this one is cyclic. We have positive, negative, positive, negative. So it's actually repeating waveform. But this one is a constant. So that's why the frequency for the voltage source is 0. So when you have a voltage source here, so meaning that this one is a DC circuit. So if you see here, what is your reactance? If the frequency is 0. 0, right? So 0. That's why, just for your information, okay, because after this we will go through more and more about the properties of inductor and also capacitor. Okay, this is just what I call just a preface about the AC circuit analysis. So in the DC circuit, the inductor is actually represented as a short circuit. So that's why, okay, inductor is short circuit. And if you have a capacitor, you have the DC circuit connected with a capacitor. Okay, so this one in the DC circuit, the capacitor is actually represented as an open circuit. So that's why in DC circuit, inductor and capacitor don't have any what we call importance. Okay, for inductor it is just a short circuit, and for the capacitor is actually open circuit. Why short circuit? Because the values of the reactance of this inductor is depends on the frequency. So if this one is a DC source, so the frequency is 0. So that's why it's actually short circuit. Okay. So right now I want to relate with the superposition. If you have this one 15 volt DC, and you have a resistor, for example, 10 ohm, and then you have an inductor, which is the inductor value is maybe 2 Henry. And then this one, you have AC voltage with a value of maybe 15 cos 15 cos 10t plus, for example, 10t. Okay, where 10 is actually your omega. So right now you have a mix of sources. You have DC source and you have AC source. So can you calculate for me the values of the reactance XL? Because XL is actually omega L, right? So can you calculate for me what is the value of your reactance? Can you calculate? Can you determine?
5.
Sorry?
1 by 2.
Your XL is
1 by 2.
1 by 2. 1 over 2. Is it? 1 over 2 ohm. Okay. Why 1 over 2? Okay. Any other answer? Your L is 2.
20.
Omega is 10. So okay, one of your friends said your XL is 20 ohm. One of your friends say 1/2. One of your friends say 20 ohm. Any other answer? You have the mix of DC and AC, right? So this omega here is 0. What is the frequency? Omega, we know that omega is 2 pi f, right? So if referring to the voltage source here, the frequency is 0. So your omega should be 0. But this one, 2 pi f, which is have been given, which is 10. So right now you have two different omega right now, 0 and 10. Which one should be the correct omega to be used to calculate your reactance? You see the problem? So meaning that this answer is not correct. This one is wrong. Because this one you are only consider AC source, right? Because you need to know that if you have mix of DC and AC, if you are considered DC, so the inductor should be short circuit, right? But if you consider AC, the inductor should be some values, which is should be 20 ohm. So contrary, because this one DC and this one is AC. So you have a value of either 0 or 20. But this is actually totally wrong. This one is not acceptable. Okay. So that is where the superposition theorem is taking part. Okay. For example, you know that superposition theorem, only one source need to be turned on, while the other must be turned off. So in this case, what you need to do, for example, if I want to turn on this one must be off. V equal to 0, meaning that voltage source here becomes short circuit. So right now your circuit is operating with a single DC source. Okay, then you can calculate your current, for example. But this one, since this is a DC source, so the frequency is 0, meaning that this one is short circuit. Okay, because omega is 0. So your current is 15 volt over 10. So you should get around maybe this one 5/2, right? 5/2 amps. So this is a DC current. Okay, this is a DC current with a value of 5/2. This is your DC current because of this one DC is actually a DC source. Then next, what you need to do is to turn on the AC, the second source, which is the AC back, and this one should be turned off. Okay, so right now you need to turn back the inductor. So the inductor, the value of the inductor XL is depends on the frequency. So right now you have a single source AC here. The voltage source is killed. Okay, so meaning that your inductor value is depends on this omega. So 10 multiplied with your Henry, 2 Henry, so you will obtain 20 ohm. Okay, so from here you will obtain the current. So the current also will be like this. So okay, this is I prime, and from the AC analysis you will have I double prime. So this one is because of the second source. So maybe your current will be like this, right? AC. So your I total should be the combination of summation of I prime and I double prime. So maybe your current will be, since this one's plus constant plus and AC, maybe it is shift up. So maybe your current will be like this. Okay, because constant plus AC, so okay, so it is shift up 5.5/2. Okay, so this is your AC waveform, the total AC waveform. Instead of using of this, okay, you sum up, you will have this. Okay, so I hope you understand. This is actually the brief, okay, about the AC circuit that we will. I think we start by tomorrow. Okay, pre-recorded. I have already pre-recorded that. About the AC, but don't worry because we will. I will actually go one by one, meaning that how this inductor is represented as a reactance and so on. And then we will also go to the use of the complex numbers. Okay. So I think in my video also, I will show you on how to use calculator in the complex numbers. I don't know, or I don't remember whether in SPM, have you already been exposed to complex numbers during your secondary school or metric school? Fundamentals?
Complex number in maths.
Sorry?
In
Complex
maths?
complex numbers.
Yeah, we have been introduced.
Okay. So meaning that it's okay lah. So and then you have been exposed to multiplications of complex number. For example, if you have J20 multiplied with J10, so what is the values? So this one have been taught. So this one should be negative 30. So negative 200, right? Have you been taught about this?
Complex number in I form we have learned.
Yeah, okay, I form, yes, I know.
Yeah.
In calculator, we are using I, right? Instead of typing like this, so in calculator is 20I multiplied with 10I, right? Okay,
Yeah.
so, okay. So meaning that you have been exposed to complex numbers. So because
Yes.
we will go through, but we will refresh back what is the complex number multiplication, how you division, how you do the what else? Conjugates, multiplication, division, addition, subtraction, and so on. Okay, so don't worry on that. Okay, so that is for the superposition theorem. We will actually meet this superposition theorem in our AC circuit analysis. Okay. So before I leave you with the pre-recorded video, so today what you need to watch is actually the Thevenin and Norton. So actually Thevenin and Norton theorem is the last part in the DC circuit analysis. Okay, so tomorrow we will discuss on several other examples. Okay, for Thevenin and also Norton, and then after that. You continue watching about the AC circuit analysis after that. Okay, that one is tomorrow. Okay, so before I leave you with the Thevenin and Norton, I would like also to highlight something about another theorem that I don't know whether it is under your syllabus or not, because based on the course information, this theorem is not under your syllabus, but I think it's better to also expose to you about this theorem, because this theorem is correlated with Thevenin and Norton. So the theorem that I mentioned is actually this source transformation theorem. Okay, source transformation. Okay, so source transformation, what is all about is actually if you have a voltage source, a single voltage source, and connected to a single resistor in series. So this one is your voltage source, this one is your R. You can actually transform this into a single source current parallel with a resistor. Okay, and if you have this circuit also, you can also transform back to this circuit also. So both circuits are interchangeable. Okay. For example, how can I transform this voltage source with the resistor into this current source and a resistor? What is the values of this current source? And what is the value of this resistor? Okay. So the value of the current source, what you need to do is actually to calculate the current here. This value of current source is actually equals to the current values that flow inside the circuit. But since this is open circuit, meaning that the current is zero. So what you need to do? So the simplest one is just short circuit. Okay. So meaning that this current is actually I short circuit because the current here that flow is actually because of you short circuit the terminal. Okay, so your I is equal to I short circuit, which is very simple one is Vs over. So your current source is Vs over R. Okay, and what about the resistor values? So actually the resistor value is actually the same. So if this one is 10 ohm, this one is also 10 ohm. So there is no change of values of the resistor. This value of the resistor is actually same. Okay, it's actually similar. There is no change in terms of the values. Okay, and what about if I have this current source and I want to transform into this circuit? How? Okay, so you can do this transformation by calculating what is the voltage across this output terminal. So this one VOC, or sometimes we also call it an open circuit voltage. Okay, VOC. So actually your VS is equal to VOC. Okay, so can you calculate the VOC here? So for okay, this is the current. So the same current will flow through the resistor because current that flow here is actually zero because this is open circuit. So there will be no current flow here. So all the current source will flow through the resistor. So your VOC is I multiplied with R. So if this is IS, so this is also IS. So this one is IS. So meaning that your VOC is equals to the values of the current source multiplied with its resistor. Okay, so this is the source transformation theorem, which is correlated with the Thevenin and Norton. Okay, so I think after you watch the Thevenin, so just give you a brief about the Thevenin. So Thevenin theorem is actually where if you have a complex circuit here and then you have a terminal output, and okay, and then your load is changeable. Okay, sometimes 10, sometimes 100, but the remaining circuit inside this box is still the same. So if you change the load, every time you need to calculate the IO, right? So if you change the load, so you need to redo the calculation, do the mesh current, nodal analysis, and so on inside this circuit. This circuit may be very complex, a lot of components here. So which is also very tedious because the only change is actually on the load side. So every time if the load change, I think it's quite difficult for you. It's time consuming because you need to do again the mesh analysis and so on to get the IO and also your VO, right? So instead of redo all the calculation inside this box, Okay, so Dividend have proposed a theorem where you can actually represent the circuit with a very simple one, which is what we call the Dividend circuit. Okay, so the resistor here is R Dividend, and the voltage source here we call V Dividend. So we can represent the compact circuit here with this equivalent Dividend circuit. Okay, so this is actually Dividend. And then the second theorem is Norton. So Norton is actually, it says that it can be represented as a current source connected parallel with a resistor. And this resistor is called R Norton. And the current source here is called I Norton. So that is all about these two theorems, Dividend and Norton. So actually it simplifies. So rather than you redo again and again, so we simplify, we can represent the circuit into a very simple circuit. So meaning that, for example, if you connected with a load that is always changed, so you don't need to do the mesh analysis so on here. So what you need to do is just, for example, to calculate the IO and VO, you just use this Dividend and also R Dividend circuit. Same way goes to the Norton circuit and so on. Okay, so that is all about the Dividend and Norton. So in the video, you need to watch how to obtain V Dividend and how to obtain R Dividend and so on, IN and also RN. And this theorem is actually interchangeable, meaning that after, if you get the equivalent circuit for Dividend, you will, from this circuit, you can transform into a Norton equivalent circuit because this is correlated with the source transformation. Okay, so that is all about the Dividend and Norton. Okay, and inside the pre-recorded video also, I have explained about one example from the slide. I think I have already posted the slide in the e-learning. I hope so. Please double check. And if I haven't yet shared, then please inform me. Okay. Okay, I think that's all from me. Any questions? So tomorrow we will do some more exercise on Dividend and also Norton. Okay, about 1 hour, and then after that I leave you with a video about AC circuit. Okay, so if there is no questions, then okay, so if there is no question, then I leave you with the pre-recorded video, okay, on the Dividend and Norton. So so this recorded video I will post after this, okay, so don't worry. Assalamualaikum and have a very good day.
Thank you, Doctor.
Okay, Doctor.